Hey everybody, welcome to Practical Alchemy. Today I am going to be teaching you how to V-Carve in Fusion 360. Now some people are going to say that V-carving in Fusion is not very good, and some people are going to say that you can't carve in Fusion at all. And I am here to tell you that that is simply not the case. Totally doable, works really well, you just have to know how to set it up. So today's tutorial is going to be broken up into two sections. In section number 1, I'm going to explain the basics of what V-carving is. And in section number 2, I'm going to show you how to set up a V-carve in Fusion 360. If you want to go ahead and jump to section 2, I've got the time code posted here. All right, so let's start at the very beginning because I have heard that that is a very good place to start. And the first question is, what is a V-carve? A V-carve, as the name suggests, is carving into a material with a V-shaped bit like you see here. The next question is, why? Well, a V-shaped bit allows you to create, in your carve, sharp interior corners compared to what a round milling bit will create. So let me show you that with a quick example. Right here, I have two rectangular pockets. And in the first pocket, I've actually already set up a couple of toolpaths. And I've set this first toolpath up with a 1/4 inch end milling bit. Okay, so it's a 1/4 inch. And as you can see, a little bit here, but I'm going to go ahead and simulate it to make it a little bit easier to see. As you can see, when I carve with a round and mill bit, the sharpest corner that I can create is the radius of the bit itself. In this case, it would be 1/8 of an inch. So even though I've got these sharp corners in the designed pocket, the tightest radius I can get is this 1/8 of an inch here. By contrast, rather than using a round end mill, if I was to use a V-shaped engraving bit, as we see in example number 2, and now I'm going to simulate that, I am able to vary the depth of the cut, thereby allowing me to create the sharp corners that I had originally designed in. The next question is, how does V-carving work? Well, in order to illustrate V-carving, I'm going to pull up example number 3. So, V-carving, because I'm using a V-shaped bit, you can imagine this as my cutting surface. Starts off very, very narrow, and the width of the bit increases as you go up the sides of the shaft, or the cutting face. So, if I go ahead and create this as a simple tool path, what you'll see here is when I simulate this, the width of the cut here, as you can see, it starts off very narrow and then it widens out. The width of the cut is determined by the depth of the bit. All right, so let's see that really quick. As you can see here in this example, the bit, I'm going to change the angle a little bit and I'm going to slow it down. The bit is going to go deeper as it goes across the cut, thereby increasing the cutting width. And then as it starts to go back up, it will decrease the cutting width. I'm going to show you that one more time in the front view, and I'm going to turn transparency on. So let's look at that again. As the bit comes down, it's going to start off with essentially a 0 cutting diameter. And as it enters the material, the cut is going to get thicker as the bit goes deeper and narrower as the bit goes back up. So in essence, it is the movement along the vertical axis, in this case the Z-axis, that allows me to change the width of the cut. For this reason, V-carving is often referred to as 2.5D carving, because while the design that you are carving is essentially two-dimensional, it's a two-dimensional sketch sitting on a three-dimensional workpiece, because the bit is moving up and down and the depth changes are creating some geometry changes, it's essentially 2.5D carving. Now, beyond just cutting sharp interior corners for things like squares and rectangles and diamonds, V-carving is also very useful when carving things like text and organic curvature. So for example, with the text, you can see, I'm going to start the simulation. With a simple V-bit, there's a lot going on here, right? There's a lot of very, very small, tight radiuses. There's a lot of detail. And because this bit is able to move up and down in the workpiece, I'm going to turn the model off so you can see it. Because the bit is moving up and down in the workpiece following the form of that letter, I'm able to create some very intricate letter shapes, and beyond that, also some really interesting organic geometry in the face of my workpiece. So typically when you're going to be carving text or small details or illustrations or graphics, you are going to be using V carving to do that. The next thing that I want to talk to you about is what type of V-bit to select. There are two primary things that you're going to consider when selecting your bit. The first is the bit angle, and the second is the bit's maximum cutting diameter. So let's illustrate these two properties with some example here. Let's first talk about the bit angle. So in the first rectangle here, I'm going to use the 60-degree bit, the sharper angle of the two. All right, and I'm going to go ahead and simulate this cut. And as you can see, I'm able to do a successful cut into this workpiece. Let's look at that again from the front view. And as you can see, this bit has to go pretty deep to achieve the cutting width necessary to create this shape. Now, let's contrast that with our next bit, which is also a half-inch cutting diameter, but instead of a 60-degree angle, the second bit has a 90-degree angle. So let's look at these at the front view very quickly just so you can kind of see the comparison. So here's our 60-degree bit. It's a very sharp angle versus our 90-degree bit, which is much flatter. All right, same rectangle, and let's create this same cut again. So as you can see, able to cut the shape pretty well, but by contrast, the depth required to create this cut is much shallower than the depth required for the 60-degree bit because it achieves this same cutting width at a much shorter depth in the Z direction. So there's advantages to both. In some cases, especially when you're going to have a lot of very tight, fine detail, it often is nice to use a sharper bit angle because you can get a deeper cut. You're going to get more contrast. You're going to get more shadows off the side walls of your cut. But if you have a thinner workpiece, you're going to want to go with a wider or more open angle because it's going to allow you to achieve a greater cutting width at a shallower cutting depth. The next thing that you're going to want to consider when selecting your V-bit is the maximum cutting width, or the maximum cutting diameter. So in this case, both the 60-degree bit and the 90-degree bit that I'm showing you have a maximum cutting width of ½ inch. Now let's look at this third diamond example. This diamond has a width of about 0.65 inches. Don't remember exactly where I said it, but it's essentially 0.65. Which means that neither of these bits is going to be able to cut this rectangle. Let's go back to that 90-degree bit one more time. And I want to show you where we are. So when I drill this bit down, this is getting very close to the maximum cutting width that I can achieve. So ½ inch here to here. As you can see, I'm going pretty deep, and I've only got maybe 0.1 or so inches left. So I don't have very much cutting face left in order to go deeper and thereby go wider in my cutting width. So in order to achieve a greater cutting width, I'm going to use a 90-degree bit with a maximum 1-inch cutting diameter, which is going to look more like this. So going back, this is a ½ inch bit, and then this is a 1-inch bit. Same cutting angle, but a much wider maximum cutting width. So let's go ahead and run this simulation. As you can see, this bit is going to come down, and it's got a much wider cutting face in order to achieve that wider depth. Now let's look at the same simulation again from the front view so we can see the comparison. As you can see, same cutting angle as my 90-degree bit, but because I've got this much larger maximum cutting width, I'm able to cut a wider triangle or a wider shape using this bit. So to recap, there's two primary factors that you're going to want to consider when selecting your V-bit. First is the cutting angle, how steep are the sides of your bit, and second is the maximum cutting width of your bit. A wider bit is going to allow you to create a wider cut. So now that we've got that understanding, there are a few other things that you need to consider when selecting your V-bit for your V Carve. And I think based off of this example here, and you can see how deep we're getting into the workspace, you can start to see what I'm talking about. Now, I'm going to show you what happens when we cut this diamond shape with my 60-degree bit. All right, so I've got this set up with my 60-degree cutting bit. And it's a slightly wider diamond shape than in the last example. I'm going to run this simulation. Let's turn the model off so we can see the full simulation. Bit is going to come down, start cutting into the workpiece, and we're starting to see the problem here. Can you see it? There's a little hole right here at the bottom. Let's look at that again from the front face. Run this simulation, bit is going to come down, and as we're starting to get a little bit wider in our shape, right there, our bit has punched through the bottom of our workpiece. Now, Fusion 360, like any software program, is only going to be as smart as you are. It's going to run the toolpaths that you set. So you have to be very careful that the maximum width of your cut does not exceed what your bit is capable of. Because if you are going to go into this situation, not only are you going to end up with a hole in your workpiece, you also are going to run the risk of damaging your spoil board. You have the potential of breaking your bit if it hits something hard inside of your spoil board. So a lot can go wrong if you don't check your simulations and check your toolpaths to make sure that your bit can handle it. Now, this particular issue can be solved pretty easily by going into the toolpath, going to edit, and rather than selecting my 60-degree bit, I'm going to go here and select my 90-degree bit. I'll select that bit and hit OK. Let's run this simulation again, and instead of going with the 60-degree bit, we now have our 90-degree bit. So running the same simulation. Seems to be cutting well. And once that completes, we are going to check it. Looks pretty good. And let's go to the front view with the transparency turned on. Check it one more time. And as you can see, I'm able to cut this shape without exceeding the maximum cutting width of my bit and without punching through the backside of my workpiece. Same diamond shape, but because I've chosen a bit with a wider angle, I'm able to keep that cut a lot shallower. Moving to the next example. Let's say I'm going to take this same diamond shape, and instead of cutting it with my half-inch bit, I set it up to cut with my quarter-inch bit. I think we know what's going to happen, but let's just see so we can confirm. Start the simulation. And what you're going to see here is that the bit is going to go all the way down to its maximum cutting depth, but what do we have here? A peak. We have a peak right in the center of our workpiece. Why? Well, because if we look at our simulation again, our bit is traveling all the way at its maximum depth, right? That's the maximum cutting width of this bit, but it's not wide enough to stretch all the way across this diamond shape. So instead, it's going to do the best that it can by going to its maximum cutting depth and then tracing the outside edges of this diamond. And what we end up with is a high spot in the center that the bit simply can't cut. So the first example, right here, we had a bit that was too steep and therefore was cutting into the backside of our workpiece. In this example, we have a bit that is too narrow and does not have the cutting width necessary for the profile that we've designed. This can be solved by checking our simulations before we cut and come up here, and rather than select my bit with a 1/4 inch, I'm going to move this up to my 1-inch bit. Select, all right, hit OK, and I am going to run this simulation again. And as you can see, I now have a bit with a wider maximum cutting area that is able to handle the geometry that I have defined in my sketch. So those are the basics of V carving. It uses a V-shaped bit in order to allow you to create sharp corners by moving the bit vertically in order to vary the cutting width. When you're setting up a V carve, you want to consider the angle of the bit, you want to consider the maximum cutting width of the bit, and you want to consider the thickness of your workpiece so that you can select your bit accordingly and ensure that your cuts are neither too deep and cutting through the backside of your workpiece or too narrow, not being able to complete the V carve. Now that you have a good understanding of what V carving is, in the next section I'm going to talk to you about how to actually set up a V carve in Fusion 360. And it's actually quite simple. So what we have here is a sketch. So we've got some two-dimensional sketches, and they're all sitting on the top of our workpiece. And this is really important. You want the V carves to be sitting on the top face. In this sketch, I've got two things. I've got some text and I've got some geometry. To create a V carve, I'm going to come up here to the 2D menu and click on Engrave. In the Engrave, first thing it's going to ask me to do is select my bit. So for this example, I'm going to go with my smaller 1/4 inch 45/90 degree V carve bit. All right, you can set the feeds and speeds. Next one is where you're going to select your geometry. When you're selecting geometry for a V carve, it has to be a closed profile. There has to be an enclosed volume that you can capture. And if you have multiple closed geometry loops, if you select multiple of them, it will essentially go on, off, on, off. So this is a closed profile, and this is a closed profile. It's going to assume that I want to carve what is between them. Next is the height clearance tabs, which you don't really need to set if you're going to allow the bit to move up and down. You just need to make sure that your clearance height and your retract heights are in the right place. Then under passes, there are not a ton of options here, but you can change the tolerance and the sharp quarter angles. You can also go multiple depths if you want to have this cut step down versus do it in single passes. And you can also adjust the stay down distance and the entry position under the linking tab. But the main two tabs that we're going to be concerned about today are the tool and the geometry. So I've selected this loop and hit OK. And let's go ahead and simulate to make sure that it's done what we've asked. So we're going to simulate this V carve. As you can see, it's found this geometry here. It's keeping the bit down, and it's carving my shape. I can do the same thing to create my text. So come up here to 2D Engrave, hit Engrave. And one thing that's really cool about Fusion 360 is if you have text sitting in your sketch, it will assume that that is all one contour. So you don't have to go through and select every single letter individually. I'm simply going to select this as my contour, make sure I've got the same bit selected, hit OK, and let's go ahead and simulate this. So transparency, as you can see, it's going to go letter by letter, and it's going to trace the inside of that geometry. You can do the same thing with not only sketches, but actual geometry in your model. So I'm going to turn these sketches off so they're not distracting. You can see I've actually cut these shapes into my model. And so if I come up here to 2D, go to Engrave, I can now select this closed loop. And I can select multiple closed loops, hit OK. And as you can see from the simulation, same thing as with the text, it's going to go through and carve these two letters. Now, if you notice here with the A, I selected two profiles. I selected the outer profile and the inner profile, and just like with the circle example, it closed this geometry and took this geometry out. So it enclosed the area between the two closed geometries. I'm actually going to go in and edit this toolpath so you can see what happens if I don't do that. I'm going to turn the model back on, and I'm going to add to my selection this R chain here, leaving out the interior. So what happens when I do that? Run the simulation again, turn the model off so we can see it. As you can see, if I don't select that inner profile, it's just going to come in and carve the outside. Because it's so wide here in the center of the R, you can see I'm getting that V-shaped tip that I got when my bit was too small. But very simple to edit. I'm going to exit the simulation, come back in, I'm going to turn the model back on, I'm going to add this inner R shape to the toolpath, turn the model off so I can see the simulation, simulate again. And as you can see, it has now correctly identified my R. Now you'll probably notice that in that example, because I had actually extruded this text so it became geometry and not text in a sketch, I had to select every letter individually because it is now, each one of them is its own chain. I can do the same thing going back here and editing my tool path. So I can go the same thing and add any other kind of geometry, not just text, but any kind of geometry that is carved into this face can be added to my selection. And you can now see that as part of this simulation, not only do I have the letters that I've selected, but I also now have this arrow shape. Very cool. And as you can see here as well, you don't have to go through and select every single thing as an individual cutting path. So I did that in this example document so that you could see and we could go through it multiple times so you can understand the process. But once you've got everything laid out in your 2D sketch, if you're able to cut it with the same bit, you can select multiple profiles as part of the same tool operation. All right, I'm going to exit the simulation, and there's one more thing that I want to show you before we end the episode. As you can see, I'm starting to get that same tip in my arrow. Now, let's say for this example, I like the depth of my text, and I really don't want the middle of my arrow to go super deep into my workpiece. Or, alternatively, let's say I've just got a larger circle in my model that I would like to V-carve. It's about 2 inches wide. There's no bit that I could find that's going to allow me to V-carve without punching through the back of this workpiece. So let's set this up and see what happens. Let's say I use that same engraving bit, that 1/4 inch 45/90 degree bit, hit OK. And when I simulate this, turn the model off, you can see I've now got this big disc in the middle. It's the maximum cutting width of my bit. How can I solve for this? Well, what we're going to have to do is we're going to have to create a flat bottom V-carve. And there is no operation in Fusion 360 to do that as a single step. We have to set that up as 2 tool paths, and we have to use a little bit of trigonometry. All right, so let's think about this bit. This is a 90-degree bit. So whenever it cuts down, it's going to cut the same distance over. If you imagine this is the workpiece. However far it cuts down, it's going to cut the same distance over. So for example, this is going to be theoretically half the width of the bit, and this up and down depth of the cut is going to be half of the cutting diameter of the bit. Okay, so let's go into our tool path here, and let's check what that is. All right, so it looks like if we go into the height, the bottom depth is about 0.11875 inches, okay? So that's how deep the bit will go at its maximum. So let's instead adjust that so it goes a little bit less than that. We're going to go negative 0.1. So ease it up a little bit and give us a number that we can easily remember. All right, so that has now decreased a little bit. And now what we're going to do next is we are going to create a flat end mill profile using the same shape geometry, but we are going to change the stock offsets in order to compensate for the V-shaped edge that we already have. So thinking about what we've done here, we have now changed the cutting depth to 0.1, so we can assume that the sidewall of this V will also be 0.1. So here's what we're going to do. Let's go back to our model, and we are going to add a 2D pocket. We're going to select this as our path. We are going to change our tool to a 1/4 inch flat end milling bit. All right. And now over here in the G Passes tab, we are going to select this option here, which is stock to leave. So what we want to do is we actually want to leave 2 stocks. The radial stock is the amount of stock off of the side of the bit. So in this case, it's going to be 0.1. And the axial stock to leave is going to be negative 0.1 because we actually want it to cut down to that depth along the axial direction of the bit, and we want to leave some material along the diameter of the bit. Let's hit OK, and let's see what that toolpath looks like. So I'm going to turn the model off, and as you can see, we're going to simulate this path and go a little slow just to show you what's going to happen. So bit's going to come down. It's a flat end milling bit. It's going to start to ramp its way in and then cut this face out. And as you can see here, I'm going to start to slow it down. It's slowly increasing its cutting depth. And right there, you can see that the end of this cut is perfectly aligned with the maximum depth of this V. And it's going to give us a nice flat surface all the way around. And with that complete, we now have a flat bottom V carve. So walking through that again, just very quickly, what you're going to do to create that is you want to select a bit, a V carving bit. In my opinion, it's easy to do it with a 90 degree because it makes the math easy. You are going to set the maximum depth in the bottom height tab here. Then you're going to create a pocket mill with a flat milling bit that is going to have a radial stock that is equivalent and a negative axial stock that is equivalent. And that is how you're going to achieve a flat bottom V carve. Now, I will tell you that there are some situations that are going to be a little bit more complex to set up, but we'll save those for a different tutorial. If you enjoyed this video, give me a like. If you had any questions or topics that you'd like to see in future videos, put those in the comments. And as always, hit the subscribe button so you can stay up to date as I release new content and you can keep learning with Practical Alchemy. Thank you so much for watching, and I will see you in the next one. And don't forget to hit save.